Manager for the AFM business at Bruker, and I would like to welcome you to the installment of Bruker AFM webinar series. This presentation is titled Technology Advances in Nanomechanics, presented by Dr. Dalia Yablon of Surface Care and Dr. Bede Pittenger of Bruker Nanosurfaces. Before I introduce Dalia and Bede, I would like to make a few quick logistical comments. First, we encourage your participation during the webinar, and if you have a question, please type it into the questions dialog box on your screen. We will accumulate these questions through the presentation, group them together, and then answer them at the end of the prepared remarks. Quite often we have more questions than we can answer in this session, and in those cases, we will be sure to follow up with an answer via email afterwards. Also, if you would like to review the presentation afterwards or pass it on to a colleague, the webinar will be posted online within 1 week in the webinar section of the Bruker webpage. As a follow-up to this presentation, you will also receive an email with this link. Finally, when you exit the webinar software, you will be asked to take a brief survey. We would very much appreciate it if you would take the time to complete this, as it helps us pick the topics that are the most important to you and to generally make this series much better. So let's get started, and let me introduce our presenters. Dr. Dalia Yablon has been working in the field of scanning probe microscopy since 1998. She is the founder of Surface Care, an AFM and nanoindenting-based consulting company in the greater Boston area. She spent over a decade developing and leading scanning probe microscopy research at ExxonMobil and edited a book on SPM and industrial applications. That's a Wiley publication if you're interested. She holds an AD in chemistry from Harvard University and a Ph.D. in physical chemistry from the Columbia University. Her area of expertise includes nanomechanical characterization methods and polymeric materials. Dr. Bede Pittenger is a senior development scientist in the AFM unit of Bruker Nanosurfaces business. He received his Ph.D. in physics from the University of Washington in 2000, but has worked with scanning probe microscopy for 25 years, building systems, developing techniques, and studying properties of materials at the nanoscale. His work includes more than 30 publications, 3 patents on various techniques and applications of scanning probe microscopy. Dr. Pittenger's interests span topics from interfacial melting of ice to mechanobiology of cells and tissue to the nanomechanics of polymers and composites. Now I will turn it over to Dalia to begin her talk titled The Quest for Quantitative Nanomechanical Measurements with AFM. Are we there yet? Dalia?
Thank you so much, Hector. It's a real pleasure to be here with you today. So as Hector mentioned, I run an independent AFM consulting company in the Boston area. And I've been working in nanomechanical measurements and characterization for about 15 years now. And what I hope to address today is really the status of quantitative nanomechanical measurements with AFM. I've been very fortunate to have to work with a number of colleagues over the years that I'd like to acknowledge here. And the work that I'm going to be discussing today has really been done with colleagues from ExxonMobil, where I was before Surface Car, and Bruker, Bede, Hector, and Thomas. So AFM is intuitively primed to make nanomechanical measurements. We've got a very sharp tip on a cantilever that's interacting in an inherently mechanical fashion with the surface. And so I've often heard that AFM being referred to as a high resolution finger, where we're really touching the sample. So it really was almost designed to make these kinds of measurements. Now, there are many ways that the probe can interact with the sample, including both resonant and non-resonant ways. Resonant, where we're oscillating the cantilever to resonance frequency. And then there are many observables that we can monitor as a result. Now, when we're making nanomechanical measurements, there are actually different challenges depending on whether you're measuring materials that are stiff or soft. So for stiff materials, you might worry about the sensitivity to the material. AFM cantilevers do tend to be on the soft side, and so sometimes you have to try some advanced modes or work a little bit harder to make sure that you get good sensitivity to stiff materials. as well as probe wear. That's another common challenge for these kinds of materials. Soft materials pose different problems, and soft materials are going to be the focus of what I'm going to be speaking about today. So for soft materials, we have to worry about the opposite of probe wear. We have to worry about probe contamination. And then these materials also can exhibit viscoelasticity, dissipation, and adhesion, which are fundamental to soft materials and can pose some real challenges to AFM. And then finally, there are some model limitations that we can have to worry about for soft materials. So I realize that my cursor may not be showing up. So let's see if I can. Okay, hopefully this is showing up now. Okay, sorry about that. All right, so AFM has been doing nanomechanical measurements for a while. And so here are just some examples of some of the initial measurements that were done in the 80s and early 90s. We start with friction. This is an example of data by Matthew Mate from 1987, where he was doing lateral force mode on graphite, scanning perpendicular to the cantilever axis and scanning in the forward and backward direction and looking at the separation to give us an understanding of friction. Here's some early first curves from Nancy Burnham on the different materials, including gold, graphite, and elastomers. This was kind of the forebearer of the force spectroscopy that we do today. And then over here, probably the most common kind of nanomechanical measurement is an example of phase imaging. And perhaps we've all kind of memorized Don Chernoff's phase image of wood pulp, where he shows some really intricate morphology on the wood pulp that does not appear in the topography. And then same that we can see here in the polymer sample. Phase imaging is probably the most common form of imaging now for these kinds of polymer materials. So these measurements are still workhorses for AFM. They are standard capabilities that are provided on all instruments, from educational and low-end instruments to our most sophisticated research-end instruments. They are fairly easy to operate. They use conventional cantilevers, and there have been really significant developments in software over the past 20-25 years that have significantly improved the user-friendliness and accessibility of these modes. But the question still remains, how useful are they for quantitative or even semi-quantitative measurements? So let's start with phase. I'll come right out and say it, not very useful for quantitative or semi-quantitative information. Phase is great as a qualitative tool. But the problem for mechanical measurements are several-fold. The first problem is that there's a convolution of multiple material properties that affect that phase shift, the phase signal that we're mapping, which means that you cannot really assign the phase contrast to an individual mechanical property like stiffness or adhesion, for example, because it's really a convolution of everything that's causing the phase shift. Another common problem for anyone who's practiced phase is an artifact and bistability problem. So we can have a lot of artifacts in phase due to the bistability of imaging in the attractive or repulsive regime. And here's an example of a sample that I imaged, identical area in the net attractive and the net repulsive regime. And clearly there's a contrast reversal issue. And the imagers are really showing and highlighting different features. So in terms of trying to interpret the phase as a mechanical property, it doesn't do very well. Like I mentioned, phase imaging convolutes a number of material properties. And so quite frankly, it's still poorly understood and very challenging to model. Here's some work I did at ExxonMobil a few years ago, where we took a very well-defined sample of 3 polymers. We imaged it under well-defined conditions, got the phase image where the one material, the polypropylene, had a phase at 45 degrees and the polyethylene at 50 degrees. Then we tried to simulate it. We used the simulation software Veda, which is out of Purdue University, And Veda had recently incorporated viscoelasticity into the model. That's usually a key missing link into a lot of these simulation packages. And we were able to input actual viscoelastic parameters collected for these materials into Veda, and we were trying to predict the phase. So how did we do? Well, we got the right direction. The polyethylene was higher than polypropylene, just like in the experimental data, but the numbers were way off, right? So polyethylene here is 30.6 degrees, where experimentally it was 50 degrees. Again, showing that we don't fully understand phase. We can't model it in terms of predicting a phase given a certain kind of material property. Force curves also suffer from this. So here I show force curves from those three polymer materials. So the red is polystyrene, the green is polypropylene, the blue is polyethylene. And there's a hysteresis between the approach and the retract curve, that gap between the approach and retract curve. It's more significant on the polyethylene than the polystyrene. But that hysteresis can really confound the application of certain contact mechanics models that we use to extract modulus parameters from this data. Additionally, force curves suffer from the need for very robust calibrations of various parameters, such as the spring constant, the sensitivity, that's the deflection sensitivity, and the tip shape. And until recently, acquisition speed was a hindrance. Force curves used to be slow. So fortunately, there has been significant progress since the data I showed you from the late 80s and 90s. We're very fortunate that there have been significant advances in hardware and software for more meaningful quantitative measurements. And I'm going to talk about two areas specifically today. One is called contact resonance, which is a dynamic contact method to probe viscoelastic moduli. And the other is improvements in speed and data analysis for force spectroscopy. So before I dive in to these research results, we wanted to do a poll. So hopefully this will work. Bear with me. What nanomechanical characterization methods are you using in your research? You can select more than one method. So please go ahead and vote. And I'm going to close the poll very shortly. Looks like people are voting, which is good. So we're going to close the poll in 5, 4, 3, 2, 1. Okay. And so I'm going to share the results. Hopefully that will work. Okay, I don't know if there they are. Okay, so you can see the results. So interesting, force spectroscopy seems to be the #1 method. Phase, very popular. I'm glad to see instrumented nanoindentation there. And a contact resonance and force modulation. We have a good amount of people doing that. So very interesting. Okay, so let's go into the results. So before I dive into research, I wanted to make sure we're on the same wavelength in two very important areas. The first one, what nanomechanical measurements are we actually trying to make? What are we trying to measure? So AFM, we're essentially working in the elastic regime, and the most common mechanical properties that we're trying to measure are modulus and adhesion. Now modulus, we need to be a little more careful because there are actually different moduli that you can measure. It's a complicated parameter. At its simplest form, in static mode, there's Young's modulus, which is simply the slope, the constant, the relationship between stress, which is pressure, and strain, which is displacement in response to that. So in the elastic regime, this slope here would be our Young's modulus. Now the modulus is complex for viscoelastic materials. And viscoelastic materials are ones where their mechanical properties are rate dependent. So for those kinds of materials, we have to talk about dynamic moduli. And the dynamic moduli are the storage modulus, or the real component, which is the elastically stored energy, and the loss modulus, shown here, E double prime, which is the viscous dissipation of energy. So storage modulus is E prime, loss modulus is E double prime, and the loss tangent is the ratio of the two. Now, you also may refer to or read about the reduced modulus, which is actually what we're mostly measuring in AFM and those nanoindentation measurements. The reduced modulus is the combined modulus of our tip and our sample, where nu is our Poisson's ratio and E is the modulus. So in all of our measurements, this is really what we're measuring. And then we have to extract out this sample modulus by knowing the Poisson's ratio and modulus of our indenter and Poisson's ratio of the sample. So it's important terminology here, and you need to make sure that you understand what modulus you're measuring and what you're comparing it to, especially if you're comparing with literature. Now for viscoelastic samples, another word of warning is you have to be very careful of the frequency mismatch problem. What this refers to is that AFM is fundamentally done at high frequencies. So the cantilevers are resonating at tens or hundreds of kilohertz if you're using a resonant-based method. Even if you're using force curves, those are typically done at a rate of 1 or a couple of kilohertz. Those are high frequencies compared to where our bulk measurements are made, like by a DMA, for example, which are typically done at very low frequencies of 1 hertz to a maximum DMA can handle is maybe 200 hertz. So that's several orders of magnitude difference in terms of frequency space that's being sampled by these two measurements. And for viscoelastic materials that depend on frequency, that matters. So what, for example, in the polymer community do, we can do what's called time temperature superposition to calculate a high frequency modulus if we know the low frequency modulus at a series of temperatures. But again, the takeaway here is know and understand the frequency of your measurement, especially if you're going to be comparing it to a bulk measurement that was done at low frequency. The second complication here in AFM measurements is that the frequency that you're doing the measurement at may not be the frequency that the sample experiences. This is especially true for tapping mode and force spectroscopy measurements, where the sample is most likely experiencing the frequency of your measurement plus higher order harmonics. So when you're trying to compare it to a measurement done at a single frequency, it's not clear that that comparison can be done. So just be careful about that. Okay, so let's talk about this method of contact resonance for mapping viscoelastic properties. Contact resonance is a method where the tip and the sample are in contact, as shown here. And so the tip sample contact is then oscillated at frequencies greater than the frequency of just the free air oscillation of the lever. So here I have a very nice simulation, courtesy of Jason Kilgore from NIST. Let's see if I can get back to, 1 second, I'm trying to get back to my pointer. So that will do it. Nope. Okay. 1 second. All right, let's just do it. Okay, let's just do it this way. Okay. And then I'll go back to the screen show. So this simulation actually shows both off resonance and on resonance oscillation. I'm going to play twice. So the first, so here we go. Okay. May have to skip this one then. Try one more time. Let's see. Okay, we're going to skip the simulation. But essentially, the tip and sample are in contact, and they oscillate at resonance. And so what happens is, while you're oscillating this tip sample contact, you collect the contact resonance tune. Let me turn back the laser pointer. We collect the contact resonance tune as shown here. And there are two significant parameters that we track or measure on this tune as the measurement progresses. The first is that frequency peak position, and the second is the quality factor. The quality factor, or Q, is the full width half max of the peak or the sharpness of the peak. And so we can model this as a damped harmonic oscillator and extract the viscoelastic properties of our sample. So there are several key advantages of contact resonance for nanomechanical measurements. The first is that we have a constant tip sample contact. It's not like tapping mode or force curve where the cantilever is out of contact, then hits the sample and then comes out of contact. The cantilever comes into contact with the sample, has a small amplitude oscillation while in permanent contact with the sample. Second advantage, well-defined frequency. We know the frequency the sample experiences because, again, it's in permanent contact, small amplitude oscillation. We know if we want to compare it to other moduli measurements at a frequency, that frequency factor is clear. And the final thing is that contact resonance closely resembles nano-DMA, so you can compare it to bulk measurements. So by tracking that Q and frequency and applying the appropriate models, you can get images such as the one shown here. So this is a blend of 3 polymers, polypropylene, polystyrene, and polyethylene. And you can see that the phase image actually shows very little contrast between these 3 materials. But then when we conduct contact resonance to measure the storage modulus and the loss modulus, we get very nice differentiation between the materials in these maps. And you can note that the Z scale now is in units of gigapascals of actually modulus units. And then we can compare the storage modulus measured by the AFM with the DMA and the loss modulus of the AFM with the bulk DMA. We can see the storage modulus does quite well. The loss modulus struggles a lot more, and part of the reason for that is that the loss modulus also primarily relies on fitting that quality factor, or full width half max, the sharpness of the peak. That's much harder to get right than just the frequency peak position, which is most of the information that goes into the storage modulus. So that work was from approximately 5 years ago. And there have been a lot of developments in contact resonance, and these are some of the capabilities to consider in contact resonance today. First, are you doing imaging or point measurements? Although imaging is more visually appealing and maybe can generate pretty pictures, imaging can wear and contaminate your tip substantially depending on how your tip is moving around. So sometimes point measurements are a much better way to go. Another important capability is your ability to collect all your eigenmodes. So just like the freely vibrating cantilever has multiple vibrating eigenmodes, in contact resonance, we also have multiple modes corresponding to those. And the ability to tune through multiple eigenmodes gives you more flexibility and improved sensitivity because sometimes some modes are better than others. Another important capability is the ability to collect your full tune. Some techniques rely on collecting parts of the tune or sampling at different points, but a full tune collection will improve your ability to quantify that quality factor, which is especially important for that loss modulus calculation. Speed, contact resonance can be very, very slow. Sometimes it makes force volume look fast. So that's also been an area of improvement. And finally, the ability to model the lever. So currently the models assume rectangular beams for the levers. So levers that are unusually shaped, you might not be able to do the calculation all the way to storage and loss modulus if it's an unusually shaped lever that does not follow Euler-Bernoulli beam theory. So some practical challenges with contact resonance. Probably the #1 practical challenge is finding your peak with a good signal-to-noise ratio. In order to achieve that, what you need is effective damping and good coupling of your sample to your actuator. So here's an example of a contact resonance tune of a cantilever on a polymer sample. Note here that we've picked up all 3 eigenmodes. going back to a point on the last slide, that the ability to capture more than one mode is very important. So we've got all three eigenmodes with excellent signal to noise, very clean background. So there's no confusion about which is your mode and which is an artifact. The second consideration is sensitivity to material properties. Basically, some modes are going to be more sensitive than others, and you have to sometimes try them out. Here we had an example where we use this mode 2 on our 3-polymer blend, and we were able to see excellent differentiation, excellent sensitivity on these tunes on the 3 different components. The final practical challenge is tip wear and contamination. And it's a significant challenge in contact resonance, and it basically requires you to reference your measurement frequently. Bede is going to be discussing this in detail in his part of the webinar, but just to give you a little bit of a taste of contact resonance with all these improvements that I just discussed, what the data might look like. And here's some data that we collected with Bruker's fast force volume contact resonance on our 3-polymer blend. This is our contact resonance frequency and quality factor. We also map the amplitude channel. And then we have our calculations of our storage modulus and loss modulus channel. So now I just want to spend a few slides on some improvements in force spectroscopy in terms of speed and data analysis. So force spectroscopy has improved significantly since the 90s and since that data I showed from Nancy Burnham's group. Right now, we have impressive control over all features of our force curves. We can separate out parameters for the approach and retract. We can customize basically any part of this curve in terms of how we trigger, off of what kind of channel we trigger, the ability to hold and do creep experiments. For viscoelastic materials, the frequencies for the that we do the measurements, and we have control over all of that. For the modeling perspective, we have significant progress in that I would say all the main contact mechanics models now are commercially available for fitting, and this has been a real improvement in accessibility for users. So models such as the DMT, JKR, SNED, and Hertz are pretty much standard parts of force analysis packages today. Of course, we have a wide range of spring constants for commercial cantilevers to sample a whole wide range of materials. And speed, right now we can do force volume with real-time acquisition speed, so that's a great plus. And so Bede is going to talk in more detail later, but this is a peak force Q&M measurement on our 3-polymer blend, and we're mapping now the modulus, comparing the DMA, bulk DMA in blue, with the AFM measurement from peak force Q&M in orange, doing quite well. But there are still significant challenges in force spectroscopy. First, we end up with large data sets. Second, the analysis can still be a real hurdle. In terms of real-time analysis, it's still done with a very limited set of models. Probably the best way to approach force spectroscopy for quantitative measurements now is you collect the data and then you do your analysis afterwards, where you have more flexibility in terms of the models you use and the algorithms that you can use for different parts of the force curves. We still are lacking user-friendly ways to use different models within the same image. So if you have heterogeneous materials, you may have some materials that might want to use a DMT model, and maybe other materials that are more sticky, for example, that need the JKR model. So you need to be able to do that within your image. And then viscoelasticity is still very challenging to model. Force curves are still plagued by significant uncertainty. That unknown tip shape size is still quite the challenge for this measurement. Bede is going to talk about some pre-calibrated probes with well-defined tip shapes that are a big help to mitigate this issue. My kind of dream or wish list is, wouldn't it be great to be able to get a snapshot or like an SEM image of the state of our probe at any point, and then have a magic wand or something quick and easy to clean it up if necessary. Another uncertainty that plagues this measurement is uncertainty in spring constant and deflection sensitivity calibrations. But a big question of this is how much uncertainty can you tolerate in your measurement? Right now, our current methods are giving us 15% uncertainty at best, right? And we're only going to get worse from there. Maybe that's enough for your application, but if not, that's kind of the state of the art right now. And then finally, there are other elements of fitting of force curves in terms of how you fit the baseline and algorithms of how you fit the adhesion that actually introduce their own uncertainty on about a 10 to 15% level. And then finally, for force curves, for those that are dealing with viscoelastic materials, be very careful when you're comparing with the dynamic moduli, because we have this question: what is the frequency that the sample is experiencing in our force curves? Just one more word about sensitivity or uncertainty in our spring constant and sensitivity calibrations. This is work that was published by John Sater last year. And they did the identical cantilever, it was a round robin, between 13 users in 6 groups. And they're calibrating the spring constant. So this is one lever, this is a second lever. The points in red are the are spring constants measured by laser Doppler vibrometry, and in blue by thermal measurements. And look at the variation. It's quite significant. I mean, if we look at this cantilever, we're seeing 50% variation in the spring constant of the identical lever, with more than a 50% variation with some of the thermal measurements and the LDV measurements. So John is trying to promote crowdsourcing of the spring constant calibration. I encourage you to read the paper if you're interested in it. And this was done for spring constants that are fairly soft. So for stiffer spring constant, the uncertainty is even higher. So in summary, nanoscale mechanical property measurements really are a critical and unique area for AFM. That's not going to change. As I said in the beginning, AFM is intuitively designed to make these kinds of measurements. We have made significant improvements in the past 20 years with strong understanding of limitations of phase, improvement in force curves and the models we use, and new methods or newer methods like contact resonance. But trying to address the issue that I posed at the beginning, what is really the status of quantitative nanomechanical measurements? Are we there yet? So I would say that accurate quantitative nanomechanical measurements that are also user-friendly and robust remain elusive. Now, there's a slight qualification to that in terms of what does accurate mean in terms of your application. Maybe a 20% error is okay, in which case you're in better shape. How much of an error can you tolerate? But I would like to look at instrumented nanoindentation. I look at that as our gold standard and role model in terms of the goals for accuracy, quantitativeness, robustness, automation, and ease of use. Instrumented nanoindentation has repeatability and accuracy within 5%. It does extremely well. Now, there are some real reasons why it does so well over, for example, the AFM measurements, including reasons such as a very well-defined probe shape that is fairly straightforward to calibrate and a regime that's much easier to model. But I still view the instrumented nanoindentation as our role model, gold standard, like I said, and we're not there yet. And part of the problems are, as we've discussed, are our models adequate? Sometimes you may have heterogeneous samples, like I mentioned. Viscoelasticity is still a problem. There are other sources of hysteresis and dissipation in the force curves that we're not incorporating. Perhaps we haven't even identified yet. And then a final problem that is particularly severe for the viscoelastic materials is comparing apples with apples. Again, you've got a frequency problem where your AFM is being done at a high frequency relative to a bulk measurement. And then for spectroscopy tapping mode type of measurements, what frequency is our sample experiencing? Is it even appropriate to compare with bulk methods? And in many cases, the answer is probably not. So I take it as good job security. We still have work to do. I've made a lot of progress, and now I'm going to turn it over to Bede, who's going to talk about some specific areas that Bruker has made some improvements in.
Okay, see if I can, here we go. Okay, thanks, Dalia. Today I'm going to discuss some of the things that we at Bruker have been doing to try to improve the accuracy of AFM nanomechanical measurements. And so we'll build on what Dalia talked about, and you'll see where we've made some progress and where we haven't. So. I'm showing you. There we go. Okay, so firstly, we need to choose the right tool for the job, and we really have quite a lot of.
I apologize. This is your tech support. Your slides are being cut off. Did you want to try perhaps showing in a different view? We're losing the right inch of your screen.
Yes. Try this again. Okay.
It looks great. Mm-hmm.
Okay, thank you. Yeah, so we want to choose the right tool for the job, and we have a lot of options within AFM. Essentially, the AFM property measurement modes can kind of be split up into some non-resonant modes here on the left, and resonant modes here on the right. And so in the non-resonant modes, the Z motion is much lower in frequency, and it is not near a resonant frequency of the cantilever, whereas in the resonant modes, it is near a resonant frequency. So typically, it would be over 10 kilohertz, often hundreds or even megahertz. So here we have this plot. We have frequency on the bottom axis and modulus on the right, the left axis, and you can see that these different modes have kind of optimal regions in the frequency modulus space. And so if you choose the contact resonance, that maybe isn't the best for doing very soft materials. Force modulation maybe is good for intermediate range, but not great for the highest materials or the highest frequencies. Force volume, peak force tapping is kind of in the middle also, and force spectra is great for low frequencies. The other thing is that the non-resonant modes allow a continuous variation of frequency, and since our moduli are a function of frequency, sometimes you would like to actually do the measurements at different frequencies, and so this allows us to have more specific control over the frequencies that we will do the measurements. First thing, choose the right tool. Second, understand and minimize the error sources that are causing us a problem with the measurement. And then thirdly, improve the modeling of the contact mechanics and cantilever dynamics that are used to calculate out these properties. If I can advance. There we go. Looks like the mouse pointer, the cursor isn't working great. Okay, so let's focus first on two of the non-resonant modes that are based on the same concept, force volume and peak force tapping, or as we call it often, peak force QNM. Force volume was developed in the mid-90s. It was one of the first, and it's still a great way to measure nanomechanical properties of samples. It works by ramping the tip up and down. This dashed line is indicating the Z motion toward the surface until it hits a trigger value, which is a maximum deflection that's allowed, and then abruptly turning around and going back in the other direction. So it has linear ramping, but it has an abrupt turnaround. That abrupt turnaround has a tendency to excite ringing in the system, and it can also cause overshoot, so that the force you requested isn't necessarily the maximum force you get if you go faster. The good thing about this is that discrete force triggers occur for each ramp, so but it also puts a limit on how fast we can go. In contrast, peak force tapping and peak force QNM were developed to overcome the speed issue with that turnaround. So we use sinusoidal ramping. Here our Z motion is sinusoidal, and we don't have problems with a piezo resonance, but we need to go fast because we're using a real feedback loop to actually control our force. So instead of trying to turn around on a dime or instantaneously during the ramp, we just look at what the error is in each successive ramp, and we adjust so that the next one will be good. So really, this is great for fast ramping, not great for low frequency ramping, but it gives you extremely low force and high stability at high frequency ramping. Whereas force volume works much better at low frequencies. But the bottom line really is that these are both collecting complete force curves for every interaction between the tip and sample, so you get a direct calculation and mapping of the sample properties. So here's an example of some very high resolution imaging in peak force tapping mode. This is mica atoms on a dimension icon, and you can notice immediately that the force is very, very stable here, and all the force curves look great. There's no ringing or anything like that at 2000 hertz. Now, force volume has actually been significantly improved in the last few years. Here's some 1 hertz ramping, which would have been very typical a couple of years ago. We like to call our faster version of this fast force volume. And really, it allows us to go up to over 200 hertz in linear ramping. Here's 150 hertz. And that allows us to overlap the peak force tapping or peak force QNM rates. So this is, I showed you, when I was showing you the 1 hertz, that was a 16 by 16. I increased the resolution on this to 128 by 128. Now you notice that the force is a bit higher on the high frequency. That's caused by overshoots. Now that would not be an issue with peak force tapping, but with very high rates in force volume, you will start to see some overshoot because it's trying to trigger on each individual curve. At least we've eliminated the ringing though. And this is really really makes it practical to do very high resolution imaging of in force volume, even greater than 512 by 512 image maps. We can also collect all the standard or all the property channels that are things like adhesion, modulus, stiffness, things like that. They're all calculated on the fly in real time, and we can get up to 12 data cubes. The raw data is all saved, so that's great. We improved the offline analysis to allow direct comparison with peak force capture or peak force tapping data. And we also have a surface hold functionality, which we'll be talking about more with regard to the contact resonance. Okay, so in terms of the calculation of the modulus in particular, let's look at how we do that, and then we'll do an analysis of the error that can accumulate during this calculation. So the first thing we do is we collect deflection of the cantilever and Z position as a function of time. And in force volume, where you're doing linear ramping, it'll be a straight line going down. You'll have a deflection versus time plot that looks like this, where it's not touching initially, and then it comes into contact, and then eventually it breaks free, and then it's off the surface again. Now, if we eliminate time out of this, then we can convert this into a force curve, which is deflection versus Z position. If we subtract off the deflection from the Z position, we can get an indentation, and then we can get a load versus displacement curve, which is essentially the same as what you would get with a nano indenter. And that can be fit with an elastic model. So that's how we get our modulus out of the measurement. Okay, in the case of peak force tapping or peak force Q&M, the data is essentially the same except for one difference, and that is that the Z position is now not a linear ramp, it's a sinusoidal ramp, and that causes some curves. In other words, the maximum force is no longer going to be pointy. As a function of time, it'll be rounded off. But once you eliminate the time out of that, you'll still get a force curve that looks pretty much identical. So if you wanted to do an error analysis on this, we can estimate it using a simple variance formula. So let's just start out with a Hertzian or DMT contact model. Then we can calculate what the force is, and we can also we can put it in terms of the deformation into the sample. The potential sources of error that we will consider are tip radius, spring constant, Z position, deflection voltage, and deflection sensitivity. And if you plug it all in, you get an equation that looks like this, where the first term is the uncertainty in the tip radius. The second one is in the spring constant. This is the term for the error in the Z. And then here we have the deflection error. And if you go ahead and you plot that up, you can summarize it this way. And note that when I made this plot, I'm using some numbers that are based on some improvements, which we'll tell you about in a moment. But in terms of the plot, you'll notice that the error depends on a choice of spring constant and set point when you're doing the imaging for a given sample. And so here we have the predicted error at the given set point and the reduced modulus here. So you can see that for low modulus samples, that the error is dominated by error in tip radius and spring constant. And now it's not always practical to go to very low modulus with a stiff probe because you get these huge deformations and you're going to lose resolution. You may also get out of the linear elastic regime. At high modulus, you're limited by error in Z and deflection sensitivity. If you instead try to keep the deformation constant, then it comes up at lower modulus, but really the minimum is kind of determined by the same thing, the error in the radius and the spring constant. And then finally, in peak force tapping, the Z error is higher than it is in force volume. That'll add around 5% to the force volume error, assuming everything is done well. So what are we doing to improve this? Well, I mentioned that those numbers were from some improvements. These are some of the improvements. Firstly, the probe or the tip radius and spring constant error are dominating the error. So we're going to start there. So we came out with some new probes for cells and a while back, and now we're actually extending that to materials. Basically, so we will have new probes that are calibrated using a laser Doppler vibrometer, and they have a well-defined tip shape. They also have a selection of moduli or spring constant for the to allow you to cover different moduli. We also have guided calibration software and some better contact modeling as well. And we implemented the spring constant since they're calibrated at the factory with the laser Doppler vibrometer. They can be scanned in by barcode, and you just choose which probe out of the box you're using, and you get accurate measurement of tip radius and spring constant. Here's the kind of result you can expect. Basically, comparing the DMT modulus map from QNM at 2 kilohertz to DMA also at 2 kilohertz. Looking at this ternary polymer blend, which is the same one Dalia looked at with polystyrene, polypropylene, and polyethylene. Except for the polyethylene, our results agree within the error predicted in the previous plot. Polyethylene has a significantly higher error than expected, but remember, these are actually absolute, or so we're not using a reference material for these calibration. We just use the barcode scanner. Now, if we do actually effectively use an internal reference by looking at the ratio to polypropylene, then that polystyrene gets down to 1%. So, and that's happening because essentially the system is actually being calibrated even better by the fact that we're using that internal reference. But the question arises, why doesn't the polyethylene match the DMA results? And we know the system is calibrated really well, so something is going wrong with the modeling. Probably it's possible that the adhesion is the issue, as Dalia mentioned earlier. Maybe we did all the fitting with a DMT model, but it could also be related to the viscoelasticity. So, and this really comes down to the fact that in some cases you need to use special models in order to get the accurate intrinsic properties of the materials. Models for force curves don't typically include time-dependent deformation mechanisms like viscoelasticity, although there are 2 references at the bottom of this slide that do actually do that. So there are models out there, they're just not incorporated yet. Another case would be if, not in this case, but sometimes your sample is not the ideal infinite half space, so basically you don't have a homogeneous sample, you've got a thin film or something like that, so you need a different model. Also, tip contamination has to be detected. We have implemented a tip clean procedure in our latest software. So you can just click and it'll go clean the tip off. With the icon, you can move the stage over to a different sample where you can clean it. But the user has to detect the problem and click on that button. Elastic limit essentially is another issue. If you put too much force on, you will end up making holes in your sample, and that really results in increased contamination, and it also requires different modeling. And then finally, a lot of times, if you have numbers from DMA or something like that, those numbers are for a bulk material. So there could be a surface layer on your sample that you're measuring with your AFM. And to try to understand if that's true or not, that would be a real measurement and might be of interest. But to understand whether it's true or not, you need to compare the properties at different deformation depths. So you can compare them using the AFM with different deformation depths by just changing the force. but you could also compare them using a nano indenter like a hydrotron. Okay, so moving on, I'd like to also spend a few minutes talking about contact resonance, as Dalia did. This is our resonance technique that is really great for high frequencies and stiffer materials. This is how it works. Essentially, we ramp Z, and we have a couple of different pixels here, A and B, and we control the force during that process. While we're at each of the different loads, loaded pixels, we send a little ultrasonic sweep through an actuator, and we look at what the resonant frequency is of the tip during that process. The challenges of this method are mainly preserving the tip, modeling the tip sample behavior, which is more complicated than it is in force curves, and calibrating all of the parameters. So it's based on fast force volume. So we do a hold, and that's represented, here we go. So we first approach the sample, then we hold, and we do a sweep during that hold on the ultrasonic actuator, and then we retract. And so we get essentially no contact during the lateral tip move. So we reduce tip wear from that. We also get more information. We get the force curve and the adhesion from the force curve, so we can actually do better modeling. And we also get the whole sweep from the frequency sweep. So we are not trying to detect where the peak is by looking at only a couple of data points. That gives us better Q measurements and also allows us to detect artifact peaks. So when we're setting up, we typically use the single point measurements on the left here, where we do a force curve with a sweep. Here we're showing 2 eigenmodes, and then we switch over into force volume, and we do mapping. And basically, it does at every pixel in the map, doing the force curve and the sweep, and then it does real-time calculations of things like frequency, Q, amplitude. You can get contact stiffness, storage loss modulus, loss tangent, etc. Okay, so here's an example using diamond tips. We get extremely consistent measurements. This is 300,000 curves and 80 engages later. And looking at this sample with aluminum and chromium films on a silicon substrate, we just get a tiny increase in aluminum and chromium moduli, but the measurement is very, very stable. Here's another example on the same sample, but looking at different loads. It takes about 30 minutes to collect one of these images. The numbers are very consistent for all modes, so that means that the contact mechanics are working well, and they agree actually within the error bars. And they also agree with the black bar, which is the hydrotron nano indenter. So we're getting really good numbers here. And it's great for, this contact resonance method is really great for stiff materials. But if you, since we already reduced the normal force and eliminated lateral forces, we can actually apply it to soft materials as well. And we can get loss modulus. So since we have the Q in the measurement and the frequency, we can actually calculate out loss modulus and loss tangent, which are things that people have wanted for quite some time. The research into the best way to do the calculation is ongoing. So we implemented 3 popular algorithms. The references are at the bottom of the page. And you can calculate out both storage loss and loss tangent from these. So here we have on the right, we have a map of polystyrene PMMA topography, and we did a false coloring with loss modulus on there. But you can also do different multiple modes at the same time. So in this case, we collected a wide enough sweep that we were able to excite the first three eigenmodes of the cantilever in contact. It turned out that the second mode of this cantilever is more sensitive to the moduli in the gigapascal range where the sample is, so it's the best choice for the measurement. Additionally, the moduli are a function of frequency, so a choice of one eigenmode or another gives a map of the moduli at whatever frequency the peak is showing up at. In the second mode, you have nice contrast of both storage and loss modulus. In the third, it's a little less contrast, it's less sensitive. And we also see some blue dots here. These are identifying points where the fitting or the modulus calculation failed to converge. In addition to helping the user understand where the calculation is failing in their map, these points are excluded from further computations, allowing for more accurate statistics. Finally, getting back to the ternary blend that we looked at with peak force QNM and Dalia talked about, we can do this in contact resonance also. So you start out with these resonant sweeps, and you can see they're nicely differentiated with the in frequency. And here's their frequency map, or Q map. The amplitude actually shows a very nice contrast as well, and those can be used to calculate storage and loss modulus. And if you do the calculations for the storage modulus, you compare them to DMA at the same frequency. So these have been time temperature superposed up to the frequency of the contact resonance. Then you actually get very, very close agreement with the polypropylene, polystyrene, and reasonable agreement with polyethylene also for the storage modulus. The loss modulus, the agreement is not as good, and essentially the PKAS method is off by about a factor of 2, roughly, for the polypropylene and the polyethylene, and it's a little bit more for the polystyrene. The YHT is better. It's using the polypropylene as an internal reference, so that one is going to agree, but also the other numbers are a bit better. But still, there is definitely room for improvement in that loss modulus calculation. So in summary, the combined the force curve spectrum modes really can measure modulus from live cells up to fused silica. Contact resonance can reach over 100 gigapascal. The chromium was at over 200. That's over 9 orders of magnitude in modulus. So it's really a huge range of modulus and frequency also. Force volume force curves are great for soft samples at low frequencies, and that's the best tool for the soft samples. Contact resonance for stiff samples. And then contact resonance is also giving us direct access to the viscoelastic parameters, whereas if you want to do that with force volume, you need to apply one of those models that's more complicated and less common, we'll put out there. Understanding the error sources that are going into these measurements really allows us to prioritize improvements to address them. So in this time around, spring constant and tip shape were the ones we targeted. They're important for all the methods, and we showed that force volume can be fairly accurate even without a reference sample. Peak force tapping is still pretty good, but not as accurate as force volume. And contact resonance really has a lot of parameters to calibrate. So we typically do those measurements with a reference material, ideally an internal reference. Now there's still room for improvement on all these methods. We need better modeling. We need more operator guidance. Essentially, how do they choose the right probe? How do they avoid getting into the inelastic regime? Starting with looking at these bad points in the maps is kind of a beginning at that, but there's definitely more room to go on that. So with that, I think I will wrap it up, and we'll take a look at a couple of questions.
Well, thank you everybody who's still hanging on. We're 7 minutes past the hour, so appreciate it. We have a significant number of you that are still listening. I would like to address a couple of questions. Well, we'll give this one to Dalia. It says, are there any limits on sample modulus that contact resonance cannot measure?
Yeah, so that's obviously a good question. On the upper limit, not really. Contact resonance was actually designed initially to try and probe stiff samples. So, you know, metals, hundreds of gigapascals are not an issue. The limitations really fall on the lower end. And in my experience, I'm comfortable using contact resonance for materials that are down to a gigapascal, so 1 gigapascal. Lower, there are problems with the models. Samples that have a lot of adhesion, where the models don't really integrate that, also will suffer. But I would say 1 gigapascal is the lower limit, and upper limit, you know, hundreds of gigapascals is fine.
Thank you, Dalia. The next one, let's go to Bede, and it says, how does frequency of approximately 2 kilohertz in PFQ&M affect the measured modulus values?
So it depends on the material. Definitely, many polymers have a lot of variation with frequency, and you can even see that if you just do measurements in P4Q&M and you compare them to force volume, you'll see variation. It could be factor of 2 or a factor of 3 in modulation or modulus. But that's a real change. I mean, these are the storage and loss modulus are functions of frequency, and that's the reality of it, and that's kind of interesting too. Now the trick is, you know, what frequency are you really talking about? As Dalia mentioned, when you're doing force curves, you could say, okay, well, I'm doing my force curves at 2 kilohertz, but is that really, should I really be comparing to DMA at 2 kilohertz? Probably not, because you're not in contact for a significant part of your force curve, and as Dalia mentioned, there's going to be essentially multiple time domains that are being excited there simultaneously. So essentially like harmonics in the sample. So it's a little less clear. You can look at the tip velocity, and that can be measured from your force curves, and you could be more specific based on that.
Thank you, Bede. Let's go back to Bede again. And it says pre-calibrated probes with a predefined tip shape and radius is a good idea, but how long when using the probes in experiments will those values hold true? Would you recommend characterizing the radius and shape again yourselves after use?
So it depends on what the sample is. These tips, because they're a little bit less sharp, they're very, very robust on hard samples, and we don't typically see much variation. Now, what can happen is the tip can pick up some material, and if there is a thin layer of polymer on your tip, then your tip is not behaving as it was originally intended, and that's where you need to go back and do a tip clean or something like that to remove that.
And let's go back to Dalia again. Where can you get access to contact mechanics models to fit your force curve data?
Yeah, so fortunately, I would say many main AFM vendors, certainly including Bruker, they have incorporated the ability to model the force curves with all these models. So, you know, first check is your actual AFM manufacturer and the software that they provide. I know Bruker does provide the ability to analyze with all the main models. If you're using a different instrument that perhaps does not give you access, I would recommend you look into a third-party software like SPIP Image Metrology. They have the ability to analyze force curves with all these models as well, and they input a whole variety of vendors. So check with your vendor first, and if not, you can look into third-party like SPIP.
Very good, thank you, Dalia. And Bede, in the sample with laser vibrometer calibrated tips, is the deflection sensitivity still being calibrated by the operator?
Yes, the deflection sensitivity is calibrated by the operator, but we have a guided method that basically steps the user through that. So it's almost automatic, but it does use the calibration of the AFM, the piezo, to calibrate that deflection sensitivity there.
And Bede, you mentioned cleaning the tip. How would one clean a tip in your system?
So one way to clean a tip would be to scan a sample that has a lot of sharp edges on it. The tip check sample is one sample that will have a tendency to remove soft material from the tip. The tips that we have that we're working with, these 30 nanometer end radius tips, have enough, they're robust enough that they can scan the tip check sample without being damaged themselves, and just the contaminant gets removed from the tip during that process.
Very good. And I think I'm going to go back to Dalia on this one, and you can certainly chime in, Bede, but high frequency can damage the tip very quickly. Will not that be a waste of tips in your experiments?
You know, the high frequency combined with the load that you're using. So both in, I don't know if they meant for contact resonance or peak force, but certainly in both of those, you are controlling how hard you're pushing onto the sample. And again, it's going to depend on the sample. So you can have a very hard sample where it might run down the tip, and then you've got, you can use diamond probes to try and prevent your tip wear. But you can also have the opposite problem of the contamination. So I would say it's not necessarily the high frequency that's the problem. It's really the sample and then the load, how far you're pushing, and how much you're sampling. That's one of the reasons I mentioned in contact resonance. You may want to consider doing these point type measurements, which is how the fast force volume is doing it, as opposed to actually scanning, which might wear down the tip more.
Okay, and thank you, Dalia. Let me go to Bede with another question, and I think we'll make this our final question because we've gone over time by quite a bit, and thank you for hanging on. In your error analysis, Bede, you showed an error that's higher for peak force tapping, and that was on slide 9. Why is that the case?
Well, peak force tapping, that sinusoidal Z motion is a little harder to get an accurate measurement on than the linear measurement that's done by in force volume. Basically, in peak force tapping, you need to both measure the amplitude and the phase of that sinusoid, and a very small phase shift can cause an increase in error, so essentially it will be a little bit less accurate just due to that. Hopefully that answers the question.
Okay, thank you, Bede. And I want to thank our guest speaker, Dalia Yablon. She is the founder of Surface Care. Look her up. She's got a lot of knowledge behind her, SPM usage and nano-indenting. Bede is our senior development scientist in the AFM unit at Bruker and has been instrumental in developing a lot of these modes. Feel free to contact him. There were many other questions. Apologies for not having the time to respond to them, but some of them were, about the availability of the presentation. We will post it on our website within 1 week. Others were questions of tip types used in contact resonance, as well as the calibrated tips for peak force tapping or peak force QNM. we will certainly reach out to you individually and give you the information. Again, thank you to the speakers, and thank you for our audience and attending this nanomechanics webinar. So long.